Okay, let's talk about the periodic table trends. All right, there are 3 trends that I'm going to talk to you about today. You need to know not only what happens as you move across the periodic table, so like what the trend is, but you need to also know what these words mean. Yeah, I'll explain it. The first thing that we'll talk about is atomic size. Okay, so I'm going to use sodium as an example. So this is my element of sodium, and here's my atom. I've got the nucleus, and I've got an electron cloud here. Do you remember what particles are in the nucleus? Protons and neutrons. Electrons are not in the nucleus. That would be a bad. So the way that we define atomic size is if you have one atom of an element next to another atom of the element, how far is this distance between them? And so we think about the size of one atom, but the way that we measure it is the distance between 2 atoms. I know that's a little bit confusing. Okay, so I'm going to do the easy thing first, and then I'll make it more complicated. I'm going to draw my little periodic table again here. When you are going down a column or a group, as you go from top to bottom, the size of the atom will increase. The way that I show that here is by using an, I'm going to write it. Normally I use an arrow that like means atomic size goes up as you go down. But I know that there are 2 arrows here, so that can be confusing. This makes sense to us, right? Because if sodium is here on your periodic table, francium should be bigger than it, right? It's got 87 protons, a bunch of neutrons, so that means 87 also electrons. That makes sense. As you go down, your atoms get bigger and bigger. Now I'm going from right to left, not left to right. So from right to left, atomic size also increases. So what does that tell me? Where the 2 arrows meet, that's my biggest element. So why is francium the biggest? Why not element 118? That doesn't make sense to me. We've got fewer protons and fewer electrons in francium than we have in oganesson. And so why would this element be bigger than Og? This is why. As you add protons, God bless you, to a nucleus, a larger magnet is created. Have you ever been to like Fleet Farm or Home Depot or Lowe's and seen the huge magnets on a stick? Do your dads have a magnet on a stick at home? Or like, have you seen like videos of a scrapyard where they have the giant magnet and it lifts up cars? You ever seen those? The more protons in an atom, the bigger the magnet. And so that means it's going to be able to attract the negatively charged electrons better. Yes? Oh, thank you. Magnet. A larger magnet is created. My bad. I got too excited. I really love the magnet on a stick. It's a really fun time. If you're ever shopping there with somebody who is like taking their time, you just get a magnet on a stick and see what's magnetic. It's really fun. Hunter? Say that again, Hunter? Yeah, that's exactly why. So what this means is that electrons in the outer shell, and Hunter used the word, so he must remember it from a different science. Outer shell electrons are also called valence electrons, or valence, however you pronounce it is fine. Electrons in the outer shell are more attracted to the nucleus. That means that the atom is going to shrink in on itself because the electrons are more closely, they want to be closer to that central positive charge. So it's just like, you can imagine it like kind of just shrinking together. So again, atoms increase in size going down a group, but, and this is the part, so this makes sense. Going from right to left, they also increase. That's the part that you have to remember because it doesn't make sense. It makes sense if you think about it chemically. It just doesn't make sense if you're looking at it like numerically, I guess. All right, that's atomic size. Any questions about that? Okay, good. The second periodic table trend that I want to talk to you about is a concept called ionization energy. So a lot of times in science, if you know what basic words mean, you can try to figure out what a concept is describing just by having like an understanding of things from before. All right, so let's talk about ionization energy. Do you know what an ion is? Ion is something that has a charge. There are two kinds of ions. There's the cation and the anion. You maybe remember that from another science, but don't worry, we'll cover that later on. So ionization energy is then the amount of energy required to remove one electron. The amount of energy required to remove one electron. All right, so now I want you to put your thinking cap on because I'm going to rationalize what this is, but you got to use your noodle. The smaller the ionization energy, and now I'm never going to write those words out again because I'm way too lazy for that. So ionization energy, i.e., the smaller the ionization energy, the less work it is to remove that one electron. The smaller the ionization energy, the less work it is to remove the electron. In the same way that, like, if you're playing football, if you have a little guy that you have to block on the line, it's easier to move him, presumably, right? Because he's just smaller. What does it mean, though, if you remove an electron? What becomes your charge if you take an electron away? Right, your atom becomes positive. All right, now is when I want you to use that space that you left on your periodic table, like in between the column top and your group name. And we're going to label our periodic table in this way. I want you to put a plus above hydrogen's column. So hydrogen will be a plus. The next column is for beryllium. He will be 2 plus. So hydrogen really is 1 plus, but we don't write that 1. So some of you, when I was checking your work, when you were writing the elemental symbols, like for example, you might have written Ag 1 plus. I didn't mark it wrong or anything, but now you know that we don't write that 1. So beryllium is 2 plus. Skipping over to boron, you'll have 3 plus. Don't put anything above carbon. Nitrogen is 3 minus. Oxygen is 2 minus. Fluorine is 1 minus, but again, we don't write that 1, so just a minus. And then remember, helium doesn't do any bonding, so 0. The reason I didn't put anything in carbon is because the items in carbon's group can be anything from +4 to -4, including 0. So it's just too complicated. Leave them blank. This is not organic chemistry, so you don't even know that. All right, so now looking at this, what you just wrote on your periodic table, and knowing what you know that we just wrote on the board, if you remove an electron from an atom, it becomes positive. Which items on your periodic table do you think will have low ionization energy? All right, let's think about this. We've got the plus things over here, like on the left side. If it's easy to remove an electron, you'll have small ionization energy. And if it's easy to remove an electron, something will become positive. So ionization energy should be on this side of the periodic table low, because it should be easy. These elements already want to become positively charged. Elements over here want to be negatively charged, so they're not going to give up that electron for nothing. So then let's write that down on our periodic table the same way we did for atomic size. You can do this on your same drawing if you have room. I obviously ran out of room. So as you go down a group, ionization energy decreases. Or the way I write it, I always put an arrow. Like I write IE down arrow because I'm too lazy to write the word decreases. Yeah. Always. Always. And on tests, you can use a note card. And you can put anything you want on it. I would highly recommend that all of this nonsense goes on your note card. In fact, I so highly recommend it, I'll tell you this multiple times. Last year, I think on the first test, I had one person not do super good on it, and it was because he did not put this on his note card, and then he didn't know what to do. I'll show you what the questions will look like in a second. Okay, so just a couple of other things. Francium is still down here in the lower left corner. Now, francium, our biggest element, will have the lowest ionization energy. What does that mean? It means that it'll take the least amount of energy to take his electron away. He just has no bleeps to give. So then, who would have the highest ionization energy? Hunter? Helium is correct. It's on the opposite side. And if we know that ionization decreases going this way, it must increase in the opposite direction. Like the opposite has to be true as well. So helium has the highest ionization energy. All right, told you there were 3. There's 1 more. And then I'll give you your homework, and we can start working on that together. The last one is called electronegativity. It has another name. It's also called electron affinity. Oh, Jake's got to get a new phone. Jake broke his phone the other day. His new one's being delivered today. He dropped it coming off of the bus on Monday night. And I've been telling this kid for like 3 months to get a new phone case. And I keep saying, add it to the Amazon cart and I'll just buy it. Or just like click buy it now because he's signed into my Amazon. Like just buy yourself a new phone. No, it's fine. It's like all coming off and everything. It's fine, it's fine. Drops his phone on the ground and it breaks. $100 later for a new one. Terrible. All right, so we abbreviate it EN or EA. They mean the same thing. But what do they mean? Electronegativity or electron affinity, and sometimes I mostly use this word, electronegativity, but I think this one does a better job of explaining what it is. Affinity is how much somebody wants something. And so electronegativity you can think of as like how badly an atom wants an element. Hang on a sec. I gotta think about how I want to explain this. It's the ability of an atom to attract electrons. But electrons it doesn't already have. So I always like to think of electronegativity or elements that have a high electronegativity as like my brother Craig. So I have a brother who is 8 years younger than me. He's a real character. He's 6'8". He's a pretty big dude. He was truant his senior year of high school. My mom was the president of the school board. I'm from Kohler. So he was truant his senior year of high school. But showing that you can do anything you want, even if you were truant in high school. He is now the manager of all the pharmacists at UW Hospital in Madison. So, good things can come from humble beginnings, I guess you could say. But my brother, when he was little, so we're 8 years apart, so that's pretty many years. My sister and I are like real close in age. Craig would always want all of the things. Like it didn't matter what Nicole and I are playing with. If we were playing with like girl stuff, it wouldn't matter. He would want what we had. And we would always have to like let him play with us because our mom just didn't want to hear any bickering. She like was just tired of the nonsense. And so if we were playing Barbies or stuff, he would have to play Barbies with us. He was just like a toy hog. And like, so you couldn't ever have nice things because Craig would just have them. So I like to think about electronegativity. He's not like that anymore. But I like to think about electronegativity as like the Craig of the periodic table. All right, so let me explain this trend for you. I'm going to draw my periodic table again. You'd think after all these times I'd get better at it. As you go down a group, your electronegativity decreases. So your trend for electronegativity and ionization energy going down a column is the same. But it can't be as easy as it just being identical, right? Everyone in group 8A has 0 electronegativity. They are the kids that have all of the toys. You couldn't have possibly anything that they would want to play with. They have everything that they need. They're not going to want any of yours. They already have all of the electrons they need. They don't do any bonding, so they have no interest in getting any other electrons. So not including group 8A, if you're going from right to left, electronegativity also decreases. Okay, so then francium, again, has the lowest electronegativity. But who now has the highest electronegativity? Who is like the absolute Craig of the periodic table? Fluorine. In fact, fluorine has such a high electronegativity that if you put fluorine and xenon, which is a noble gas who has no interest in bonding, if you put them in a reaction vessel at a very high temperature and pressure, you can get fluorine to take xenon's electrons away. So fluorine is like the bully of the periodic table. It doesn't matter how much you have, he will want more. He just wants that one last electron. So that's the highest electronegativity. Remember, these have no electronegativity. And when we go through some of your homework examples, I'll show you why that's important. All right, so where did I put them? One moment. All right, I'm going to give you your homework. I'll see where the flavor trend because it's a single sheet and that never happens. It would make me anxious. Does everybody have one? No. All right, so let's take a look at this. I want to do some of these examples for you so you know what you're doing and so I don't have to answer a million questions. All right, so let's look at question number 2. Question number 2 just asks you to use all of the elements. So I've listed there all of the elements that start with the letter C that are on the periodic table, which are nonmetals. Oh, it's good we did this because I forgot to tell you about this. Here's your periodic table. The staircase, everything to the right of it is a nonmetal. Everything to the left of it is a metal. And if you forget this, just look someplace on this side of the periodic table and you'll see like metals that you know, like iron and silver and gold. Those are metals. So that's how you can remember that these are all metals. And then if you are touching the staircase, you're called a metalloid. You have properties of both metals and nonmetals, and so you're a metalloid. And then 2 other things that I forgot to talk to you about. Do you see on your periodic table that there are 2 rows on the very bottom? Those rows are there so that the periodic table fits on one piece of paper because they're really elements taken from here. And so if we didn't have this, your periodic table would like have this, and then there'd be this long line here, and then more, and then it would look like this. And so, for the sake of space, we've got these two columns on, or two rows, sorry, on the bottom. The top row is called the lanthanides because they come after the element lanthanum, which is element 57, I think. Yes, element 57 is lanthanum, and then 58 is on that bottom row. And so those are the lanthanums. And then the the actinides are that bottom row because they come after the element actinium. So that's element 89. And then 90 is the next one on that bottom row. Okay, so number 2, like which are lanthanides? Well, if I look at my periodic table, cerium is a lanthanide, so Ce, and that's it. For E, which ones are actinides? Well, curium, Cm, and californium, Cs. So that's all you got to do for that. That's how you would complete that number 2. Yes, sir. Oh, thank you. The transition elements are in this section right here. So those columns that we did not number. So those will all be like your metals like copper, cobalt, chromium, cadmium. Did I get them all? Chromium, cobalt, copper, cadmium. And then Copernicum, Copernicium, Cn. What did you say? Dominic, did you have a question? Okay.
So,
Yeah. No, if it's not touching the ladder, it's a metal. If it's on either side, it's a metalloid. So it has to be touching the line. So like look behind you, Jared. Arsenic is a metalloid. But arsenic is As, but Se, selenium, is not a metalloid. All right, gents, thank you. Okay, so do you all see that arsenic is element 33? Arsenic is a metalloid, but selenium is not. Because only its corner is touching the staircase, it's like not on the staircase. So it has to actually be touching the staircase. Yes, Elliot. Say that again. Are the A elements, are the A groups. Yep, the main groups are the A groups.
So it'd be like carbs and
Yes, carbon and calcium. There's another one. Oh, 2 other ones. Cs, yep, cesium. And then there's another one too. Look on the very far right. Chlorine, yep. All right, give me just 1 second. I can't remember what we're doing on Friday. Oh, lecture. Okay, so then we do have to do this. All right, so let me just help you answer questions like 4, 5, and 6. 4 asks me to circle the smallest atomic size element. All right, so what you're going to have to do is find these elements on your periodic table and use your trends to help you decide which one is the smallest. All right, so I'm looking at my periodic table and I have to find phosphorus. Phosphorus is right underneath nitrogen and he's right here. Silicon is right next to him and calcium is way over here. Okay, so which one is the smallest? Well, if we know what our trends are, atomic size decreases going from right to left. I'm sorry, increases. Oh my Lanta, what a day I'm having. So that means that your smallest friend will be on this side of the periodic table. So P is what you'd circle. Does that make sense? Elliot, did you have a question? All right, so let's do B then. Titanium, cobalt, and zirconium. All right, so titanium, cobalt, and zirconium. All right, so where do you have to look for the smallest one? To the right or to the left? To the right. To the right. So who's the smallest? Cobalt is the smallest. All right, I'm not feeling confident about this. Let's do something on number 5. 4A is P. It says to circle the one that has the smallest size.
Can we do all of them?
No. Okay, but I'm going to do, this is number 5A. All right, so I'm going to find sulfur, which is like here, argon, and tellurium is here. So it's asking me to circle the one that has the lowest ionization energy. Down a group, ionization energy decreases, and from right to left, it decreases. So if you're looking for the smallest one, which corner do you have to look for? Bottom left. So just find the one that's closest to that. So here you got a little bit of a pickle though, because, oh, well, I guess I didn't draw it to scale, that's why I have a little pickle. Sulfur and tellurium are in the same column. So which one of these three is closest to francium? TE. So that's your answer for 5A. Does that make sense? All right, I want you to save the back page for next time. So you can try it if you want to, but people have a really hard time with increasing size and decreasing size. So I'll help you with that on Friday. The first 1A is alkali metals. Let me know what questions you guys have.